So hi all. Very good evening and welcome back to the third week of weekly TA live sessions for the course AI Knowledge Representation and Reasoning. So, first of all, is my audio clear and is my screen visible? Can anyone just confirm? Okay, that's great. Thanks a lot for confirming. So, yeah. So, this week we'll be discussing some questions from week 3 of the course. Uh, for which the deadline I assume is the deadline for the assignment for which I assume is tomorrow. So yeah, without any further delays, let's get started for today's questions. And I remember some of the queries or doubts or requests for examples that were raised in the previous live session. So uh, I believe that as we discuss the questions for this week, those doubts or queries will somehow be addressed uh, on its own. So I hope that is the case, and if that is not the case, we can have a discussion again towards the end of the live session. All right then. So yeah, let's get started. This is the first question for you. Let the set of atomic sentences in propositional logic be P, Q, R, and S. Okay, so you are given a set of 4 atomic sentences in propositional logic, and you have to decide which of the following 4 options are sentences of propositional logic. Okay, so this is a conceptual question based on what you might remember from the course videos about what is a sentence in PL. So I'll give you a couple of minutes and then we can discuss the solution. Okay, so that's great. Some of you have already given the answers in the chat box, and yeah, all of you are correct. And yeah, so A in fact is the sentence in propositional logic over here because so if you look at the structure of each of these options one by one, right? So the first sentence says that if P and Q together are true, then that implies R. Okay, so P and Q imply R. But in the second option, option B, we see that there is a parenthesis right before an AND operator, which is not the meaningful way of writing a sentence, right? And an operator should connect two of these atomic sentences. So option B is incorrect. Then as for option C, we have an AND and an OR operator written side by side, which is also incorrect. So option C is incorrect. And then option D does not have any proper operator between R and S, right? So we have the negation operator over here, which is a unary operator, not a binary operator. So option D is also incorrect. So the correct option is option A. Okay. Any doubts about this question? Okay, that's great then. It was also a straightforward question. Let's move on to the second question. Now consider you are given this particular knowledge base. Okay, this knowledge base has a certain set of facts in it. For example, the first fact is given by P or not R. Okay, the second fact is given by R and T. The third fact is given by W implies S, and the fourth fact is given by P and S together imply Q, and the last fact is T implies negation of S. So given all these facts in the knowledge base, which of the following 6 options can be derived from the knowledge base? Okay, so again I'll give you a couple of minutes to try to, so you can try to work it out on your own, and then we can have a discussion on the solution. Okay, so we already have a couple of answers, and now let's look at how we can arrive at this solution, right? So let me shift to a whiteboard. I hope you can see my whiteboard. Give me a moment. Yeah, yeah, yeah. Okay, thanks for confirming, Nikhil. Yeah, so these are the different facts that are given to us, right? So the first fact given is P or not R. So can we reframe this and write this in terms of implication? Remember that, yeah, that is one way. Another way we could write this is not R or P, right? In that case, what would it be? Exactly. This is one way of writing this implication. So remember, A implies B is equivalent to not of A or B. Okay, these are the same thing. So this is what we are using over here. And in the second fact, we have R and T both, right? So we can say that R and T individually would also be true, because R and T together is true. Then we have W implies S, we have P and S implies Q, and T implies not S. So using this R implies P and R, can we make any deduction? P is true, right? So we can say that P is true. Okay, what else can we deduce over here? Exactly, T implies not S. So we have T over here, and T implies not S. So we will have, using these two, not of S. right? Now we have not s, and we also have w implies s. So can we deduce something from these two? Exactly, that's correct. So we can use these two to derive not of w using modus tollens. Okay, now is there anything else that we can derive, or are we done? Let's have a look at the answers and check for ourselves. So as it happens, we cannot derive anything else. So we have already derived p, we derived not of s, and we derived not of w, right? So these three are the correct options, A, E and F. Any doubts in this question? Sure, let's go over it quickly one more time. So see, we had these few facts to begin with, right? These were the ones that were given to us. Now what we will do is we will rewrite some of these facts to suit our interest, right? Firstly, we have P or not R, which can be just rewritten as not R or P, okay? Which means R implies P, remember, as per this thing, right? So we have R implies P, and then we also have R and T, okay? So we know that all the facts present in the knowledge base are supposed to be true, and for R and T to be true, both R and T should be individually true as well, right? Because when the AND operator has to be true, both the uh, entities to the left and right of it should also be true, right? So R and T individually will also be true. Now using R implies P and R, using modus ponens, we can write that P is true, okay? Similarly, using T and T implies not S, again using modus ponens, we can say that not of S is true. Now using not of S and W implies S, we can say that not of W is true using modus tollens, which is if A implies B and not of B, then we can deduce that not of A is true. Okay, this is modus tollens. So we derived P, not of W and not of S. I hope that helps. If not, it will become further clearer as we see one more example of a slightly different knowledge base. Okay, so it's a slightly different knowledge base. We have P implies P or not S, we have S and W, we have W implies not P, and we have P and S together imply Q. So in this knowledge base, which of the following can we derive? Using this knowledge base, which of the following can we derive? So again, I'll let you work it out for a couple of minutes and then we can discuss the solution. Okay, so we have one answer that says B and D. Okay, so let's look at the solution. So I'm not writing it out on the whiteboard for this one, but if it's not clear through the discussion, then we can go for the whiteboard solution as well. Okay, so again we have P or not S, which is basically S implies P, right? You agree with me? Right? We can write not S or P as S implies P. Can we write that? Yeah. And now using S implies P and S and W. Okay, so we have S and W together to be true. So S should be true as well, right? And W should be true as well. So using S and S implies P, can we say that P is true? Yeah, right. So A will also be an option. Now, now we see that P is true. Okay, but we also have W implies not of P, right? And not of P can be written as, or P can be written as not of P, right? If I just write it out, P can be written as not of P, right? So using the fact that we have P and we have W implies not P, can we derive something? Remember modus tollens, yeah, that's right. We can derive not of W, right? And yeah, yeah, that's correct. That's very correct. So negation P will also be true in this case. Thanks for that, Ariman. So we also have that negation of P is also true here. Yeah, that is leading to a contradiction because we have P to be true and not P to be true. But this is where the difference between a human and a logic machine comes in, right? So it doesn't care about whether you are arriving at a contradiction, right? Whatever it can derive, it is going to derive, right? And this also somehow correlates with the concept of soundness and completeness, if you remember from the previous live sessions discussion. Okay, there's maybe one more thing that we can derive. No, so we are not talking about the soundness of the knowledge base. We are talking about the soundness of a logic machine that we are using. Yeah, that's right. We can also derive Q. So we already had P and we had S, and together we can, using P and S, we can also derive Q. Right? So let's have a look at the solution. So as we see, we can derive all of these options given over here. We can derive P, we can derive S, we can derive Q, not P, not S, and not W as well. Sure. So remember we had derived P, right? Using this W implies not P and not, and wait, let me check. Let's actually, yeah, let me write it down. I think that would be clearer. So we have P or not S, which is basically S implies P. We have S and W. We have W implies not of P. We have P and S together imply Q. Okay. So using this we can say that S is true, W is true. Now using these two we can say that, sorry about that, P is true. Okay. Now using this P and this S we can say P and S is true. Okay. Now using this P and S and this implication over here we can say that Q is true. Is that better? Yeah. Vignesh, I didn't say that P is equal to negation of P. I said that P is equal to negation of P. P is equivalent to negation of P. Okay, this is somewhat similar to in arithmetic when we say minus of 2. What is that? That is equal to plus 2, right? It's something like that. It's analogous to that. So are there any further doubts in this particular question? No, Nikhil. P and not P are not part of the knowledge base. They are part of the facts that we have derived given the knowledge base. Okay, the knowledge base only consists of these 4 facts that are given to us. That is written at the top. Okay, now using some logic reasoning machinery that we are employing, we are deriving a set of facts. Okay, it just happens to be that we are able to derive both P and not P. Okay, which is leading to a contradiction, but that is not our concern as of now. Our concern only is what are the things that we can derive given a particular knowledge base using all the ways of reasoning that we have learned till now in the course. Okay. Yeah, so if you look at the uh, if you happen to have already looked at the course videos for this particular week, or even if you haven't, there you will come across something called the tabular method. Okay, and it's there where these kind of contradictions, presence or absence of these contradictions, will be helping us prove something about the something called a model. Okay, so we will see some questions based on that as well as we go further into the questions for today. And also if you have a look at the course videos, this concept of whether a contradiction being present or absence will be of some use to us. Okay then, I hope this is clear, and let's move on to the fourth question. Right, so I was talking about a model right now, right? So a model for a set of statements S in propositional logic, and which of these following options best suit the definition for a model? This is again straight from the course lectures, so yeah, I'll give you a minute or so to think about it, and then we can look at the solution. Okay, so we already have a couple of answers. So yeah, you are correct. A model for a set of statements S in propositional logic is a valuation for the atomic propositions that makes all the sentences in S to be true. Okay, so yeah, so the first option, if we have a look at that, it doesn't make sense. A model does not exemplify how the statement should be written. It also does not exemplify how the statements in logic can or should be written. It is also not a valuation of the atomic propositions that makes only a certain part or half or a fraction of the sentences to be true. Okay, if it makes all the sentences true, then we call it a model. Okay, this was straightforward, straight from the lecture slides. Shall we move on to the next question then? Okay, so this is where we come across the tabular method that I was referring earlier, right? So if you remember, in a tabular method we do something called eliminating a connective from a sentence. Okay, so when we do that, which of the following do you think can happen? Okay, so we have a couple of solutions. I'll give you a hint. So think about what can happen when there will be an or connective, and think about what can happen when there will be an and connective. Yeah, so when there will be an or connective, we are going to extend it into branches, right? Whenever there is an or connective, there will be a further branching. However, when there is a and connective, there will be a linear extension, right? So we cannot say that it's all the time that a linear extension happens, or it's all the time that further branching happens, right? Because we can have a situation where we have only ors, or we can have a situation where we have only ands, right? So, and or we can have a situation where we have a mix of ands and ors, right? So the correct answer in this case would be C and D, right? Eliminating a connective from a sentence results in further branching for some connectives and results in linear extension for some other connectives. Okay, we did something like this in the examples that we solved just now a while back, right? If you remember, we saw that S and W together are true, so we can linearly extend it and write that S is true and W is true, right? If we had to extend an or, then we would, then something like A or B, we would have written that either A is true or B is true, so that would result in a branching over there. Okay, shall we move on to the sixth question then? Right, so uh, you can also have a look at the example that sir presented in the lecture videos, but now for now let's take a simpler example. Okay, so for example, we have something like A or B is one fact that is given to us, and let's say C and D is another fact that is given to us. Okay, so what we do is we try to simplify it in our way. Okay, so using this C and D, we will remove this and we will say that both C and D individually are also true. Okay, and then we have A or B, right? So we can remove this and we can say that either A or B is true. Okay, so this led to a branching. Okay, we are simplifying whatever we have at hand. Okay, and in tabular method what we do is we have a look at all the branches that we have arrived at. Okay, whether it resulted as a whether it was a result of a linear extension or it was a result of some branching, we have a look at all the branches present in whatever we have till now, and if they happen to have a contradiction, then we can make a deduction about whether the problem at hand is satisfiable or unsatisfiable based on some conditions. Okay, we can also deduce whether problem at hand is a tautology or not. Okay, we can make several deduction by looking at the fact whether there is a contradiction in a particular branch that we have arrived at. Does that help, Aryaman? Okay, that's great. So the next question is somehow related to what we just talked about. So in the tabular method applied to a given knowledge base, which of the following do you think is correct? When will we have a satisfiability, when will we have unsatisfiability, and when will we have a tautology? I'll give you a couple of minutes to think about it and then we'll discuss. Yeah, hi Soundarya, please go ahead. Uh, okay, 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 okay. No, see, okay, let me just verify once. This is not in the current assignment in any way, right? Is it? Can you hear me? Yeah. Yeah, yeah. So I just wanted to confirm whether this is not present in the exact form in the current assignment, right? Yeah, yeah. I can tell you that, and if we have not B, yes, we can do that. But see, A can be representing anything, P or Q or R, or P and Q and R, anything it can be, right? Similarly, B can also be representing anything. In in any case, whatever A represents, whatever B represents, modus tollens will hold, and you can apply it to that whole thing. So that I let you infer, okay? Because since this may be present in the assignment, you are saying so. Let's wait for this, and we can discuss it in the next live session. Okay? But so I'll also give you one more hint. Then think about the De Morgan's law. Okay? So there is something called the De Morgan's law, right? So you think about whether that can be applied or not. But yeah, I can't give you any more help than that, because this, as I said, this might be there in the assignment. Okay. Okay. So coming back to the question 6 that we were discussing. So yeah, some of you have given the correct answer. So uh, when we apply the tabular method to a given knowledge base, okay, so first of all, what is meant by satisfiability? Does anyone know or would like to share their thoughts on what it could mean? Yeah, yeah, that's correct. Uh, and yeah, that's correct. I can't say it's wrong, but maybe something more simpler. So in that case, a cyclical question could be, what is a model then? Right? So uh, what can we say? Can we say that if for a given assignment of truth or, yeah, true or false values, yeah, exactly, like you said, Nikhil, at least one valuation of the sentence statement has to be true, right? So one of these branches of what, or one of the branches that we are referring to over here, that Smarak said would have to be, at least one of them would have to be a model. That will be a model will that when one of the, at least one of the valuations of the statement is true, right? As we also saw in one of the earlier questions, right? This one, a valuation for the atomic proposition that makes all the sentences in S true. Okay, so if we have at least one branch that does not have any contradictions essentially, and we also have arrived at the end of all possible expansions that we could have done, okay, and that branch does not have any contradictions, and we also cannot expand it any further or simplify it any further, then we can say that since there is at least one such branch, we can say that it is satisfiable. If all such branches are present, all such branches do not have any contradictions and all such branches do not have any possibility of further extension or simplification, then we can say that it is a tautology. And if all branches happen to have contradiction, so whenever there is a contradiction in the branch, we will close that branch, we will not extend it any further, right? So that is what is referred to in the last option over here. If all the branches have contradictions and as a result of that they are closed, we will say that it is unsatisfiable. Okay, so in a tabular method applied to a knowledge base, at least one branch should be a model for the knowledge base to be satisfiable. All branches should be models for the knowledge base to be a tautology, and all branches must be closed or must have contradictions for the knowledge base to be unsatisfiable. Is this clear? Any doubts in this question? Okay, that's great then. uh, let's move on to the seventh question now. And okay, so the seventh question. Yeah, yeah, please go ahead, Smarak. uh, so see, the when you talk about satisfiability in itself, it means that there is some valuation that makes the whole thing true together, right? So even if there are some parts of a particular set of statements that is false, that has a truth value of false, if it's making the whole uh, set of statements together to be true, then it's okay. Okay, just the moment when we encounter a contradiction, we close that branch and say that it is yeah, we say that particular thing is not a model, right? And if all the branches have contradictions, we say that it is unsatisfiable. I can actually show you an example from the lecture slides. Just give me a moment. I'm just trying to find the lecture materials, and also in case some of you didn't know, so this is where you have the videos usually, right? We also have lecture material over here, and if you click on this, you will be led to uh, the slides for that particular week. Okay, so I'm just trying to find a simple example. Yeah, over here. So here we had something, right? We had P and P implies Q in brackets, and this together implies Q. Okay, we start by the negation of the statement that is given to us. Okay, add the negated goal to the set of premises in the tabular. Okay, that's how we start the tabular method. Okay, so we simplify that further. Okay, because if the negation of this will be, so negation of A implies B will be what? Negation of not of A or B, right? So if we simplify that further, it will be A and not of B. So that's what is present over here. We have P and P implies Q and not of Q. Okay, now if you further simplify this, we get P and P implies Q. Okay, and we already have P over here, right? So P and P implies Q gives us Q. Okay, and we see that Q and not Q are present, So this leads to a contradiction. This branch is closed. Okay, and we also happen to have not p because of p implies q. Okay, or we can also use modus tollens over here. P implies q and not q together give us not of p. Okay, but we also have p, so this branch is also uh, closed because of contradiction. And because all of these are branches are closed, we can say that the negation of the goal that we started with does not have a model. So the actual goal that we started with, that is sound. Okay, which is this. So this is a simple example that was covered in course. Okay, that's great. All right then. So let's come back to the seventh question for this week, which is given the propositional logic language defined in the course, is it possible to have a knowledge base for which of the following do you think could be possible? Okay, so I'll again let you think for a couple of minutes and then we can discuss. Okay, so as some of you have already answered, the correct answers are A, B, and D, and that is because let's look at the options one by one. Option A says there is only one linear branch in the entire tabular. Okay, every node has exactly one child. This is basically an example of a case where there is, let's say, only and connectives and the uh, things that are given to us and the facts that are given to us. Okay, so there will only be one single linear extension. Okay, another is there are no linear extensions. Every node has exactly two children. Okay, this is the case where there are only OR connectives present. Okay, so any simplification you try to do results in a branch because of only OR connectives being present. Then the last option says there are no extensions and there are no children. We already have the set of facts in the most simple form that we could get, right? So there are no extensions at all, and there are no branches, no linear extensions, no children. Okay, so this is also possible. The third option, however, is not possible because some nodes cannot have three children because we are talking about binary connectives over here, binary and unary connectives, right? So they need to have one for one operator or one operand for a unary connective and two operands for a binary connective, right? So we cannot have three children. A branch can result in two children only. So option 3 is, or option C is incorrect. Is that okay? Should we move on to the next question? Okay, that's great then. Let's move on to the eighth question. Okay, so this looks like a bit of a long question, but it's actually very simple. Okay, so let me just read it out for you. So we have let alpha, beta, gamma and delta be formulas over the set of propositions p, q and r. Okay, let alpha and beta and gamma and not of delta be a simplified notation for the conjunction that is given over here. Okay, alpha and beta, which is in brackets, then and of gamma, and then and of not delta, and this is in propositional logic. So given the conjunction as input, the tabular method can be used to show which of the following. Okay, so this might look a bit tricky, but it's actually a very simple conceptual question. So I'll let you think about it for maybe a couple of minutes and then we can discuss. Okay, so we have received a couple of different answers, and so even though the formulation of the questions looks a bit lengthy, the simple point that we need to consider over here is that using the tabular method, what are the results that we can arrive at? Okay, so as we said, in the tabular method we start with the negation of the goal. Okay, we start with the negated goal, and then we have a look at whether there are any branches that have contradictions. If there are contradictions, do all the branches have contradictions? In case all the branches would be closed and it would be unsatisfiable, do we have at least one branch that does not have any contradiction and that also cannot have any further simplification or extension, in which case it could be called a model, right? In that case, that would be satisfiable. So we can say using the tabular method whether it is satisfiable or unsatisfiable. But in order to say whether it is a tautology, we have to go one step ahead, right? So since we are starting with the negated goal, for the goal itself to be a tautology, we have to prove that the negated goal is first unsatisfiable, right? If the negated goal is unsatisfiable, then we can say that the actual goal is a tautology. Are you with me? Do you understand that? Yeah, sure. I understand it can be a bit tricky when I feel so while saying it. So when you start with the tabular method, right, you start with the negation of the goal, right? Are you with me on that point? Okay. Now, when you have to say, when you have to arrive at a conclusion whether the goal is a tautology or not, it will be a tautology when the negation of the goal is unsatisfiable, right? So, what is a tautology? That is always true, right? Irrespective of what configuration you give to the elements of it, right? So, if the negation of the goal is unsatisfiable, that would imply that the goal itself is a tautology. Do you get that now? Yeah. So the basic point that this question is trying to convey is that you can, using the tabular method, you can say easily whether something is satisfiable or unsatisfiable, whether something is a tautology or not. To arrive at that, you have to go one step ahead, right? So that is why this question asks us the tabular method can be used to show that. So the two options correct in this case would be the conjunction is satisfiable or the conjunction is unsatisfiable. Okay, we will not be able to say whether the conjunction is a tautology or not just using the tabular method. Okay, we have to finish the tabular method and go one step ahead to prove that it is a tautology. It's just a small nuance to this question. That's what this question is trying to convey. Is that clear? Okay. Yeah, sure. So essentially what I was trying to say is, when you use the tabular method, okay, you expand all the branches possible, whether it's linear extension or a branch extension, and do all that. You simplify it, you extend everything, you check whether there are any closed branches, in which case that branch would have a contradiction. Okay, if it happens to be the case that all the branches are closed, which means that the thing that you are trying to arrive at is unsatisfiable, that thing that you started with is a negation of the goal. Okay, and because the negation of the goal is unsatisfiable, the goal itself is a tautology. So the point that this question is trying to ask is that using the tabular method just by itself, we can say whether something is whether the conjunction is satisfiable or unsatisfiable. If we have to say whether it is a tautology or not, we have to go just one step ahead of the results of the tabular method. Okay, so this is a very small nuance to this question. We can obviously say eventually whether the conjunction is a tautology or not, but just using the results of the tabular method, we have to we can say whether it is satisfiable or unsatisfiable. Okay, so I hope that makes it somewhat clearer. Okay, that's great. So Nikhil, we cannot say that. So this conjunction can be anything, right? We have said that alpha, beta, gamma, and delta are formulas over the propositional logic, over the propositions P, Q, and R. So they could be anything. They could be P and R, P implies R, P implies Q. They could be anything, right? So this is a generalized question in a way. If you are given a certain configuration or the exact formula that alpha, beta, gamma, and delta represent, then we can arrive at a particular answer, whether it is satisfiable, unsatisfiable, or tautology. Yeah, that's great. Then if this is clear, then we can move on to question 9. Okay, if in a tabular method, if no branch of the tabular being constructed for a formula alpha is closed, it means that we just discussed that no branch is closed. Which case would that represent? Yeah, in that case alpha would be a tautology. Or will it be? So remember the discussion that we just had. Yeah. Right, so just like in question 8 we discussed that exactly we start with a negated goal, right? So we can say whether it is satisfiable or unsatisfiable. If we have all the branches that are closed, then the negated goal is unsatisfiable and the goal is a tautology. But if we have some branches that If we have no branches that are closed, then that means that it is satisfiable. The negated goal is satisfiable. Okay, I hope this was also clearer. If not, I think the next question will resolve all doubts that are remaining about satisfiability, tautology, contingency, and all those things. Okay, so this diagram over here, this small diagram consisting of A, B, C, and D, this is like a Venn diagram. Okay, and this represents different subsets of the propositional formula. Okay, so some of these are representing tautology, some of these are representing contradiction, some of these are representing contingency, some of these are representing satisfiable, and some of them are representing unsatisfiable formula. We have to assign which of these four regions A, B, C, and D correspond to which of these cases. Okay, so I'll let you think for a while. Yeah, so one of them will be a tautology, Ritu. We have to identify which of them is it. Okay, yeah, that's right. So as Marak also said, uh, we can assign B or C as per our convenience. Okay, B or C could take multiple assignments. So good question, Nikhil. So contingency is basically something that has some valuation for which it is true. Okay, so you can use satisfiable and contingency kind of exchange in simultaneous or as synonyms of each other, if you may. Okay, so let's have a look at the solution. So we can assign the compartment D to be unsatisfiable formula. Okay, that is separate on its own. Okay, let's say D is unsatisfiable. Now the other part is that is equal in size to, or that looks equal in size to D, is A, right? A consists of B and C. I'm not saying that A and D are necessarily equal in size, but we have D, which let's say represents the unsatisfiable things, and we have A, which consists of B and C in turn. Okay, so what could A represent? Yes, it can represent satisfiable things, right? Now among the satisfiable things, there could be some things that are tautology. There could also some things that are not tautology, right? So if something is a tautology, it will also be satisfiable on its own, right? Because satisfiable, for something to be satisfiable, it needs to have some assignment or some configuration that makes it true. Tautology for sure has some assignment that makes it true, right? So D is unsatisfiable because D is a thing on its own, right? It's a disjoint set. So we can say that D consists of unsatisfiable or contradictions, which is the same thing basically. We cannot say that unsatisfiable has a subset within itself, right? At least based on what we have learned in the course till now, right? So we have one disjoint set that is unsatisfiable or contradictions. We have one set A which consists of all the satisfiable things. Within satisfiable things, there is a group, let's say B, that is a tautology, or uh, we can also say that C is a tautology. In that case, the other part of the other subset of A, B, or C would be a contingency or satisfiable. Okay, is this clear? Okay, that's great then. That leaves us with the last question for today. So here you have a kind of a practical example, or a natural language sentence, set of sentences in natural language that are given to you, and we have to represent it in propositional formula. Okay, so we have been given atomic sentences. Okay, consider the following atomic sentences and the proportional representation or propositional representation as propositional variables. Okay, so C represents the statement that, or the sentence that, Bob can make a call. D represents the battery is dead. H represents Bob did charge the battery. Z represents the balance is 0, and T represents Bob topped up the phone. Now we are given 5 formulae, okay, for 5 sentences, which are as follows: Bob cannot make the call, the balance is non-zero, if Bob does not charge the battery, then that is dead, and so on and so forth. 2 more sentences, right, or 2 more formulae. We have to represent this in terms of C, D, H, Z, and T. Okay, so how will you go about doing that? I'll give you a couple of minutes and then we can discuss the solution. Okay, so let's start with one of these sentences one by one. Right, let's consider the first one, which is Bob cannot make a call. Okay, so how would you represent this, let's say, in terms of C? C refers to Bob can make a call. So how would you represent Bob cannot make a call? It's just the opposite of C, right? So can you use a negation over here? That's right. We can represent the first one as Bob cannot make a call as not of C. Right? Then let's consider the next one, which is the balance is not 0. Okay? Which is negation of the statement Z, which is the balance is 0, right? So the second one would be not of Z. Now let's consider the third one. The third one is if Bob does not charge the battery, then it is dead. So if we look at it in 2 parts, okay, so the first part is Bob does not charge the battery, okay, which is not of H, okay, and the second part is the battery is dead, which is D. So statement 3 can be represented as not of H implies D. Okay, let's consider the fourth statement. If Bob tops up the phone, then the balance will be non-zero. So again, we can see it in terms of 2 parts, right? The first part is Bob tops up the phone, which is basically T, okay, and the second part is the balance is non-zero, which is not of Z. So if we combine these two, T implies not of Z. Okay, and let's consider the last statement, which is if the balance is 0 or the battery is dead, then Bob cannot make a call. So this has three parts. First is the balance is 0, okay, which is Z. Second part is the battery is dead, which is D. Okay, and remember there is a or between these two, right? So we have Z or D, and on the other side of this word then we have Bob cannot make a call, okay, which is not of C. So we will have Z or D implies not of C. Okay, so I'll let this remain on your screen for a while and you can have a look and convince yourselves that this is in fact the correct representations. And that brings us to the end of the questions for today. Yeah, Ariman, please go ahead. Mm-hmm. Yeah, sure. Do you have a specific question that you would like to discuss? Okay. Which one would that be? Okay. Let's look at them. Mm-hmm. Okay, let's look at them one by one. Okay. So the first thing says that A says that, aha, look there, that bear is eating honey like yesterday and the day before. So the bear eats honey, right? So here what we are doing is we are looking at some uh, observations, that we saw that the bear is eating honey today, the bear also ate honey yesterday, and also ate honey the day before, right? So we are making a generalization based on these observations, and we are saying that because the bear ate, or because we saw the bear eating honey for 3 days in a row, the bear must eat honey forever, right? So this is an example of induction. Are you with me for this one? Okay, now let's look at B. This says that the doctor said that regular exercise improves health. Okay, now I am jogging for an hour every day, therefore my health will improve. Okay, so let's simplify this a bit. Okay, the doctor said that regular exercise improves health. Okay, this you can represent it in terms of an implication. If regular exercise, then improved health, or you can write it as regular exercise implies improved health. Okay, the second part is now I am jogging for an hour every day, which can be said to be the same thing as I am doing regular exercise. Okay, so we have two parts. Okay, we have regular exercise implies improved health, and we have regular exercise, right? So this is in the formulation of modus ponens. Therefore we have improved health, right? So this is an example of deduction. Are you with me? Yeah, and just for the sake of completeness, let's look at C also. So look man, top cyclists have low resting heart rate, and he has a low resting heart rate, therefore he must be a top cyclist. So what would this be? What do you think? Okay. Yeah, so we can formulate it this way. So low resisting heart rate implies top cyclists. Can we say that? So let's say P refers to low resting heart rate and Q refers to top cyclists. Okay, so we have P implies Q, or low resting heart rate implies Q, which is top cyclists. Yeah, so let's say we have low resting heart rate, this is one part, right? And we also have top cyclists have low resting heart rate? Okay. So, okay, the answer is given as abduction. So let's think a bit more about it. It seemed like it would be a deduction. Yeah. Okay. So let's think a bit more about it. Um, okay, so someone is saying that top cyclists have low resting heart rate. Okay. Uh-huh. So the way I perceive it is that what we were trying to do, right, is we were trying to draw the implication in a reverse manner, right? We were saying that low resting heart rate implies top cyclist, right? But if we look at it from left to right, top cyclist implies low resting heart rate, right? Because that's the flow of the sentence. So let's say top cyclist represents P, okay, and low resting heart rate represents Q. So we will have P implies Q. Are you with me till this point, Ariman? And then the second thing that we are given is he has a low resting heart rate, which is Q. So we have P implies Q and Q, right? Yeah, so using that we can hypothesize that P might be true, but it's not necessary. So that's why I think abduction is given as the correct answer. So this is something that I also learned. Thanks for pointing it out. So in such cases, it's better to read the flow of sentence in the way it is given from left to right, right? Because that will help us make proper conclusions. Okay, great. Thanks for pointing it out. I think this will also help others who might be having a similar doubt. Yeah, exactly. As Nikhil said, they could have low resting heart rate due to a number of factors. Swimming could be one of them. Okay. Anything else that you would like to discuss? Okay, sure. Uh, in this one, the answers would be available if you just click on this thing, right? So, you want us to discuss it? Okay, yeah, sure, we can do that. So, ah, so this one we discussed, right? You're saying you missed that live session, is it? So have you checked out the recording of that particular week? It's up on the channel. If I don't know if you have checked it. Not really. I mean, if it's benefiting everyone, then I don't mind discussing it. But sorry. But yeah. Uh, no, if you have already seen that, if it's still unclear, then we can discuss it. But I just wanted to know if you have already seen that. Okay, then why don't you maybe have a look at it? And if it's still unclear, then we can discuss it again. Would that be okay? Okay. Yeah. Which which question would that be? Can you point me to the question number? 11. Okay. What do you recall about physical symbol systems? A physical symbol system defines the necessary reasoning procedures for an AI agent. Doesn't seem to be correct. A PSS is a set of symbols and a set of rules to manipulate those symbols. Seems logical. PSS is derived from the three laws of robotics stated by Asimov. Okay, so yeah, the second option seems to be the most appropriate for this question, right? And I assume this is a straight recall question from the slides. So that answers it. And which of the following are not physical symbol systems? A spring balance used to measure mass and grandma's watch. Yeah, that's about right? Because Wolfram Alpha and GPT-4, all these things, I think, use symbols and stuff, sort of those sort of things to represent certain statements or facts. I think these are based on the lecture slides itself, right? So I hope if you look at that. So what is a physical symbol system? What do you would you like to share your thoughts on it? Yeah. So you start by telling. Let's start by discussing what you think of it, and then we'll modify the understanding as per your requirements, right? So just by the name, physical symbol systems, what do you think it could represent? Right. So there's a hint in the name itself, right? There are physical symbols and there's a system, right? Yeah. So could we say that a system where we have symbols representing certain uh, facts or statements, and a system where we have certain set of rules, or let's say logic machinery, to reason about those symbols and arrive at certain deductions or things like that, would that consist of a physical symbol system? Okay, so yeah, I would encourage you to. Uh, I might be half correct or half wrong or completely incorrect, right? I'm solving it along with you. So I would encourage you to revisit the lecture slides once more and also revisit these links that are given over here. I hope those will be helpful as well. And see if what we discussed would be correct over here, right? If that is the case, then look at the options that are given over here. Okay. Anything else that you would like to discuss? Okay, sure, go ahead. Yeah, yeah, yeah. No, so see, the way we define or is that or statement will be true when either A is true or B is true or both of them are true. So when you're representing it in terms of two children or two branches where each of them are true, so let's say A or B, right? For A or B to be true, one of the branches has to be true. So if you look at the first branch, which where A is true, there we proceed with the assumption that A is true. If we look at the other branch where B is true, we proceed with the assumption that B is true. So does it matter if both of them are true together? That's well and good. But we can denote that only by two children or two branches itself. Does that help somewhat? Okay. Anything else? Yeah. Week 2, question 5. Yeah, snapdragons bloom only in winter. Snapdragons are in bloom and it is winter. Yeah, so thanks to Aryaman, we just saw an example of this kind of situations, right? It's better to read the sentence in the direction of the direction of the flow of information that is given to us, right? So we are given snapdragons bloom only in winter, right? So the flow of information is snapdragons bloom winter, right? That's why it is B implies W and not the other way around. Yeah, the direction in which the information is given to us, we need to follow that. Okay. Anything else? Uh huh. Yeah. Mm-hmm. Uh huh. Sorry, can you come again? You mean to make the truth table of the things on the two sides of the equivalence? You mean, right? Yeah, that is a absolutely proper way of arriving at these. But the issue with that you might come across is that if it's something very complicated, then you'll have to make a large truth table. That's the only drawback of it. Otherwise, it's a proper yeah, absolutely perfect way. You could simplify the things on the left and right hand side of the equivalence, right? And if you're able to arrive at a situation where simplification results in the two sides being exactly the same, then you don't even have to check the truth table. Okay. Mm-hmm. Yeah. Yeah. For this particular example, you can just see it, right? So whenever you have P to be true, you will have Q to be true, and whenever you have Q to be true, you will have P to be true. So these both go hand in hand, right? So P and Q are equivalent. You can derive just by looking at this particular option. So this is also one way of doing it. You don't also have to like manually write it down and try to simplify it. Yeah, I was just trying to say that if you consider the first option over here, you can just have a look at it itself and say that this will be it, the correct answer. So there can be such cases as well where you don't actually have to manually write down the things on the left and right side, left side and the right hand side of the equivalence, and simplify it by hand is what I was trying to say. Like there are some cases like this particular option where you can just have a look and say that yeah, this will be true. Yeah. Okay. Anything else? Okay, if not, um, then we can end the session for today and we can meet next week. Thank you. Thank you for attending. And yeah, so Aryaman, please try to have a look at the doubts that you were asking about. If it is not clear and you would like to have it discussed even before, you can just send an email to me and we can discuss it offline as well. Okay. Okay. So thanks everyone and see you next week.